Hello, I'm Michael O'Connell, and in today's video we're going to be deriving the heat diffusion equation for our Cartesian coordinate system. This video will be particularly important in the subsequent videos in which we use the heat diffusion equation for this specific playlist I'm making regarding heat transfer. So right here I've drawn a very simple controlled volume that's three-dimensional. We have a cube. And I first want to talk about just heat flow in the x direction. So we have heat flow q sub x entering this face of our cube here, okay? And then we have heat flow exiting the cube on the other side, of course, still in the x direction. Here, we need to do a Taylor series expansion, and for this derivation, we are actually just going to do a linear approximation. We have to do this because the heat flow need not remain constant as heat moves through this controlled volume. You could have a reaction inside this controlled volume in which heat is generated, maybe an exothermic reaction. Or you can also have heat stored, which would increase the temperature of this material that comprises your controlled volume. So that's the reason we need to do this. So of course, what goes in must come out. So you have this heat flow in the x direction that went in. But you also have to add on, you have to account for how the heat flow changes with respect to position, okay? So you have that partial derivative there. And then you also have to account for the distance that you moved through our controlled volume, okay? So this term is multiplied by the differential change in x, okay? And of course you can do this for the y direction and the z direction as well. To keep the overall equation simple, I'm only going to account for the x direction for right now. So when we are deriving the heat diffusion equation, it's fairly simple because it's really just an energy balance. So when we're doing this energy balance, I've already used all the terms, I think. You have the energy that goes in minus the energy that goes out. We want to add any energy that's generated inside of our controlled volume. And all of this is going to be equal to the energy that's actually stored inside of our controlled volume. Okay, and we have equations for these that, of course, I'm going to discuss here. And I already mentioned the concepts associated with them, but specifically, let's talk about energy generation. I can rewrite this somewhere else. Energy generation is expressed as a rate, okay, and that's what the little dot is. And of course, this has the heat here in this term. The interesting thing about this term is that this is the heat generation rate per volume, okay? So if you like units, heat generation rate, so it's per time, and you might have meters cubed to keep everything in SI units, okay? So what do we have to multiply this by? For our Cartesian coordinate system that I've drawn, fairly simply, we have a cube. So here you would have dz, this is end of the page, and then this, I'll just draw it here, I just don't want people to get confused, but this is the differential change in the y direction upwards. So we could call this dv, but the differential change in volume is just the product of all these derivatives and all three directions there. Okay, so this is the rate of energy generation, so that is right there. Now, what about the rate at which energy is stored? Okay, so that's a rate as well. What do we do for this? Well, we have the density multiplied by the heat capacity. And here we have to account for how the temperature changes as well. Okay, what are the units for this? So we have kilograms per cubic meter. This is what I do too, especially like right now when I'm like not fully recalling what the actual equation is. This is your heat capacity at constant pressure, okay? And remember that solids and liquids, like perhaps our controlled volume, we don't have to necessarily account for the changes in the specific heat. So we can just use the specific heat at constant pressure. Okay, and that's because they have small specific volumes. So what do we have here in terms of units? Well, this cancels, okay? And then we have our time unit with the temperature unit going away here, right? So we have Kelvin over seconds. Okay. So what else do we need? In case for someone like me who forgets very often, I actually crossed out the wrong thing, but you would have joules over seconds, and then the meters cubed again. So I already figured out what term I forgot. That would be dV, the differential change in volume, which I just said is the product of dx, dy, and dz. Okay? So excellent. And again, this is the important term here. This is what I used in my speech, before, like right at the beginning of this video, right? Because I said if energy is stored, maybe at a certain rate, inside this controlled volume, that will manifest itself in the material increasing its temperature, okay? Because it's storing the energy, so that has to manifest somewhere, right? And so your material heats up because less heat flow would exit in that case, but that would only be if you, again, that'd be ignoring any heat generation, of course, as well. So you have to be careful. You have to account for everything. So let's put this all together. We have our equations. We can actually write the heat diffusion equation for the Cartesian coordinate system we have on the board here. So the energy going in is Q sub x. The energy leaving is Q sub x as well, plus this term where we account for how the heat flow may change with respect to position. Okay, and of course we multiply that by the differential change in our position. Okay, then we account for any heat that's generated. I'm going to use dV for now, just because I'm running out of room. And then we have to account for the energy that's stored, of course. So this has our density of the material, and then the change in temperature with respect to time, of course, and then also the controlled volume. Okay, so we have some cancellation here. Okay, be careful, this negative term would have to distribute. Okay, so we're left with this term here. So in order to make progress in this derivation, there's really only one term I need an equation for here. I should write that. This is Q sub x that we are taking a derivative of with respect to position. And we need an equation for this. Unfortunately, we do, and that is in the form of Fourier's law of heat conduction. Okay? So when we're talking about Fourier's law, or when we're talking about heat flow in the x direction, this would be the heat flux, okay? So per unit area multiplied by the area, okay? And Fourier's law has an expression for the heat flux in the x direction, okay? This will account for the thermal conductivity of the material. Sorry, I went out of the frame there a little bit. Okay, and we also account for how the temperature changes with respect to position. Okay, so that is what we're doing when we're using Fourier's law of heat conduction. Now, if we want the heat flux, we're multiplying by the area. We're taking a controlled volume that's real small, right, in our material because we're trying to get a sense of things, and especially of how things change in 3 dimensions. So this is your surface, right, that I've scribbled over here. So that's not dx, that would be dy time, oh, that's the wrong direction. That'd be dz down here, and then dy. Okay, so for us, the heat flow, so I'll get rid of the dashes there. That would be dy dz, okay? And again, with Fourier's law of heat conduction, you have this negative sign here, okay? This heat is leaving. It's flowing from one place to another. Why do I emphasize this? Well, basically for myself, because I'm trying to derive this equation, and I don't want to forget this negative sign because we have a negative sign here as well. So we don't want to forget that. Okay, so this term here is going there. So how do we express that? Well, as I said, now it's positive. Okay. And remember that we had the dy and dz, and then we also had the dx in the original term. But this is all of this expression. We were seeing how the heat flow changed with respect to, I drew my thing there wrong, with respect to x, okay? So this was q sub x, right? Okay, this term. So what do we want to do here? Well, we can simplify this a lot, of course. This here is the differential volume, and that will come out of your derivative here. Okay, again, because we did that original linear approximation, we didn't get to higher order terms, nor did we consider how the heat flow would change with respect to the other directions as well. So that comes out, and then that cancels because you can divide across. Okay, so that's excellent. And then we're left with this, so we would express this really as it is. I'm going to use a special case that is used so often, in which the thermal conductivity does not actually depend on position. That's not always the case, but it gets extremely complicated if that is the case. So that comes out of the derivative as well, and what we would be left with is the second partial derivative of temperature with respect to position. So I'm going to write that on the board here as well. And we are really in the home stretch here, because this simplification will lead to the heat diffusion equation that we're going to be using in the next video. And what we can do here is we can divide each term by the thermal conductivity. And the last thing that's special here is this term right here. So we have a new term, alpha, which is the thermal diffusivity. It's very hard for me to say that correctly. I don't really know why. But this expression accounts for how the temperature or the heat diffuses through a material. Okay? So, of course, this accounts for your thermal conductivity. Okay? So, how much energy it takes to heat up your material based on the mass of that material you have. But what the thermal diffusivity actually accounts for is how your temperatures are changing. Okay? So how that heat is actually being propagated through the substance. So if you have a bar here and you start heating it, it's not what fire really looks like. But how is this propagating through your substance? If this is all at room temperature 20 degrees, you have 80 degrees Celsius, does it diffuse very quickly? We could derive the units for this, but it's meters squared per second. Okay, so it is a rate of diffusion. Okay, so that's the thermal diffusivity. So we would have the inverse of alpha here. So for the end here, I want to leave you with the actual heat diffusion equation for Cartesian coordinates. Notice that we would have these second derivative terms for each direction. Okay. But I'm just going to leave it in the x direction because that's what we're going to use in the next video anyways. Okay, because we're going to be looking at the temperature profile and how the temperature changes with time and position for just a bar that we are heating up. So it sounds pretty simple, but it actually gets pretty complicated. And this would be your heat diffusion equation. Of course, this only accounts for one dimension in the x direction. If you were accounting for the entire controlled volume, you would just have these second partial derivative terms with respect to y and z as well. Okay, and I don't think I really need to write those, but this is the expression you need to know and be familiar with. And I hope that this derivation is helpful and gives more context to the following videos I'm going to make, in which we look at what becomes a much more complicated problem. But I'm very excited to make those videos, so I hope you'll stick around and watch those as well. Thank you so much for watching, and I hope to see you next time.